guys, hopefully this method of doing notes for you is going to be a little bit better. You can see things a lot clearer by doing it this way, so I hope this helps. Our next chapter is on similar figures. So we just finished talking about congruent shapes. So congruent shapes have same size, same shape, everything about them is literally the exact same. The sides are the same length, the angles are the same measure, and they look the exact same. Similar figures are similar. They're not congruent. So we need to talk about what does that word similar mean. Well, if you look here, the groups of shapes on the left, it says these figures are similar. They're all rectangles. And there's something special about them though. These are similar. These triangles over here to the right, they are not similar. So even though they are the same triangles, or they're all triangles, something about them just looks a little bit different. Like this bottom triangle here looks like a little skewed from the other ones. Here, these rectangles look lovely and nice, and there's a word that I'm looking for. Maybe you're thinking about it right now. So let's go ahead and fill in the definition of similar figures. It says two polygons are similar. Now let's talk about the word polygon here for a second. A polygon is simply just a shape with the prefix poly means many. So it's a shape with many sides. Okay, so two polygons are similar if and only if the corresponding angles are congruent and the measures of the corresponding sides are proportional. And that's the word that I was thinking of to describe this group of shapes there was proportional. It's like if you take a picture. Well, it's like if you take a house and you shrink it down to size and make a model of it, everything stays within proportion to one another. Now the angles stay the same, so you got to think about this. Every triangle ever has 180 degrees inside of it. So no matter how big or small it is, it can never exceed or be below 180 degrees. So that's why the angles are allowed to be congruent, but the sides we say are just proportional. Now, the symbol for similarity is just this little squiggly there. So it's kind of like congruence except no equal sign. So the way we say this is triangle ABC is similar to triangle DEF. Okay, using this example, oh, and that's also called, remember how we had congruence statements for congruent triangles? This is called a similarity statement. So if I ask you to prove something is similar and write a similarity statement, that's what it looks like. So let's look at this example. These two triangles here are similar. You see how they look lovely, and even though they're not the same size, they're the exact same shape, corresponding angles are congruent. Okay, so that means angle A here is congruent to angle D, and angle C is congruent to angle F, and that must mean angle B is congruent to angle E. So the angles are the exact same. Corresponding sides are not congruent, because if they were, then the triangles would be congruent. Corresponding sides are proportional. Proportional. So that means segment or side AB is corresponding and proportional to DE, and so that's these two. And BC corresponds with EF, and those are proportional to one another. And lastly, AC corresponds with DF. Okay, so that's what it means if two shapes are going to be similar. Now let's talk about something called a scale factor. A scale factor is essentially if we want to change the size of a shape, then we do that by the use of a scale factor. So if a scale factor is greater than 1, then the shape enlarges, or it gets bigger. If a scale factor is less than 1, then the shape shrinks or gets smaller. Okay, recall the scale factor is what we multiply the size of a figure by to, remember back when we talked about translations and rotations and reflections, those, you slide a shape, you flip it, you rotate it, those things. There was another one that was not isometric where it changed the size of it, which was called to dilate a shape. So in order to dilate a shape, that's where we use the scale factor. So look at example A. So it says we want to find the dimensions. So for A, if I use a scale factor of 2 and I go from this quadrilateral here, it's just 4 sides, so quadrilateral, to this one, essentially what I'm going to do is literally multiply everything by 2. So if I do that, that means the side on the left, that's 7, times 2 will be 14, and this one will be 14. And then 9.5 times 2 will be 19, and 4.5 times 2 will be 9. So you multiply everything by 2. For part B, it says using a scale factor of 1/2. Okay, so what that's going to do is when you multiply by 1/2, what you can remember is that multiplying by 1/2 is the same as just dividing by 2. So if multiplying by 1/2 is the same as dividing by 2, it's a little bit easier to think of that way, because then if I just think of dividing everything by 2, then that's a lot easier. Then 6 divided by 2 is 3. So this side is 3, and this side is 3. 8 divided by 2 is 4, and this one's 4. And then 10 divided by 2 is 5 and 5. So when you see fractions, if you don't like to think about multiplying by fractions, think about dividing by that whole number. Okay, and then lastly, it says similar figures are enlargements or reductions of each other. The amount of enlargement or reduction needed to change one figure to the other is called the scale factor, which we just discussed. And the ratio, that word's important, the ratio of the lengths of the corresponding sides of a figure, of similar figures, is called the similarity ratio. Similarity ratio. So the word ratio is important because all a ratio is, well, that's on the next page, so let me wait. A ratio is simply a comparison, right? Like wins to losses, the number of boys to girls. We use ratios to just compare things in math. So a ratio is a comparison. Now, in math, a comparison compares two numbers by division. By division. It is written as, we can write it as a fraction like A over B, or back when you learned about ratios, we also learned that we could do A to B written like with a colon, or we could literally write the word 2 by saying A to B. Typically the one we're going to write though is A over B in fraction form, so you're going to see this one mostly. We won't really use the other ones. Now, a proportion, we used this word on the last page when we said proportional. So a proportion is the equality of two ratios. In other words, I'm going to have two ratios set equal to each other. So can you give me another representation for the number 1/2? So hopefully you thought of something like 2 over 4. Isn't that also the same thing as 1/2? So this would be this together would be called a proportion. Two things that are equivalent but they just look a little bit different. 1/2 is equal to 2/4. So what we're going to do is determine whether or not figures are similar. We've got to check the following things. 1, all of their corresponding angles are congruent. 2, all of their corresponding sides are proportional. All of their corresponding angles must be congruent, and all of their corresponding sides must be proportional. So let's do some examples. It says, tell whether or not the triangles are similar. So we need to check things. Let's check, are the angles congruent? So angle A is 33 degrees. So looking at the second triangle, so A is 33. Angle D is 33 degrees. So angle A is congruent to angle D. Angle B is 129 degrees. So angle B is congruent to angle E because it's also 129 degrees. And the last angle, angle C, is 18 degrees, so it is congruent to angle F. So that's good. The 3 angles are congruent to each other. Now, we're going to look at the corresponding sides. So AB, let me choose a different color here. AB corresponds to which side? Now, if you have a hard time envisioning the triangles being flipped in your brain, remember this. Notice AB is the smallest side, right, of this triangle. So if it's the smallest side of this triangle on the left, it must correspond to the smallest side of the triangle on the right, which is 16. So AB must correspond to DE. And let's look at what other ones correspond. Let's look at the next one up. Or let's look at the biggest side. AC is the biggest side in the left triangle, it's 10. So AC corresponds with the biggest side in the other triangle, which is DF. And then the last side, BC, corresponds to EF. Okay, so now it says write an extended proportion of ratios using the corresponding sides. So what that means is a proportion is just a fraction is equal to a fraction. So if it's an extended proportion, that means it just can be more than 2 fractions. So what that means is AB corresponds to DE. And if these figures are similar, that ratio should equal AC corresponding to DF, and that should equal BC corresponding to EF. Now notice when you write this proportion, all of the sides on top come from the triangle on the left, and all of them on the bottom come from the triangle on the right. So when you write a proportion, you can't mix up some of them from the left being in the numerator and some being in the denominator. It has to be consistent. Now, let's substitute the length of the sides. So what is the length of AB? Well, AB is 4 over DE is 16. And we want to know, is that ratio equal to, so I'm going to put a question mark, is that ratio equal to AC, which is 10, over DF, which is 40, and is that ratio equal to BC, which is 7, over EF, which is 28. So we want to know, are all these things equal? Well, if you simplify that, if you simplify all of those fractions, you're going to get 1/4 for the first one. 10 over 40 is also 1/4, and 7 over 28 is also 1/4. So since they are all the same, since the sides are, well, then we can say the sides are proportional. Sides are proportional since the ratios simplify to the same number. So that's how we know the sides are proportional, because the ratios, when you divide these 3 numbers here, They simplify to the same number, which is 1/4, or you could have also just done it in decimal form, and you would have gotten 0.25, which is equal to 0.25, which is equal to 0.25. So either way, they were all the same, proving that they are proportional. So then once you determine that things are similar, then we can write a similarity statement. So to do that, remember that just says triangle blah, blah, blah is similar to triangle blah, blah, blah. So let's say triangle ABC is similar to triangle. Now go up here to the top where you already wrote out which angles corresponded to each other and then name the triangles accordingly. So we know angle A corresponds to angle D, B corresponds with E, and C corresponds with F. So there's the similarity statement. The next part says, to find a missing side of similar shapes, we can set up a proportion and solve. So the most common method of solving proportions, which is something you're probably familiar with, is cross multiplication. Cross multiplication. So let's do a few examples. We're going to solve for x in each of these following scenarios. So for part A, if I'm going to solve for x, I'm going to cross multiply. So I'm going to multiply the top part of this fraction on the left times the bottom part of that fraction on the right. So I'm going to do 4 times x and then 8 times 3. So 4 times x is 4x equals 8 times 3, or 3 times 8. It really doesn't matter the direction that you do it. So then that's going to be 4x equals 24. And then if I divide both sides by 4 to get x alone, I end up with x is equal to 6. For example B, let's cross multiply again. So if I multiply 9 times 10 and 6 times x, then I get 9 times 10 equals 6x. 9 times 10 is 90 equals 6x. And again, to get x alone, I'm going to divide both sides by 6. And then if I divide 90 divided by 6, I get x is equal to 15. For example C, if we cross multiply, I get x times 4 and 36 times 9. So x times 4 equals 36 times 9. Oh, my color didn't change. So it's going to be 4x equals 36 times 9 is a very large number that I didn't calculate yet. I think 270 something. 324. And then if I divide both sides by 4, I end up with x is equal to 81. Now, you could also solve these in some other ways. So for instance, let me write my answer first. X equals 81. For instance, if I look at this problem differently, you might notice that there's a pattern in the numbers. So you might say, okay, to get from 36 to 4, all I have to do is, well, actually, let's go the other way, because the other way is a little bit easier to see. And it doesn't matter the direction that you go. You might say, okay, to get from 4 to 36, all I need to do is multiply times 9. So then all I need to do to get from 9 to x is multiply times 9. And 9 times 9 is also 81. So that's another way of thinking about the problem when the numbers work out well like that. Okay, the next 3 have triangles. So instead of just having the proportion, you have to set up the proportion. So let's do D kind of in that logical way. You might say, okay, the triangles are already in, I'm going to say, good positions to where the corresponding sides match. Like I can already tell 12 corresponds with 3, 20 corresponds with x. So then you can say, okay, how do I get from 12 to 3? All we do is divide by 4. And then to get from 20 to x, all I need to do is divide by 4 as well. So then 20 divided by 4 is 5. So that must mean x should equal 5. So sometimes it's easy to see it that way. And you could do the same thing for the next triangle, but just to show you other ways that you can solve. If I were to set up a proportion, I like to set them up like this, like little triangle over the big triangle. So remember, when you set up your proportions, you have to be careful. You can't just mix up the numbers any way you want. So I'm just going to pick any side from my little triangle, let's say 6. And I'm going to put that over its corresponding side in the big triangle, which is 24. That's going to equal the other little triangle measurement, which is 9, over its corresponding side in the big triangle, which is x. And then once they're set up like this, we can cross multiply like usual. 6 times x, 24 times 9. So that's going to be 6x equals 24 times 9 is 216. 216. So then if I divide both sides by 6, I end up with x is equal to 36. Now, this is not the only way you can solve that problem, and maybe some of you have figured that out. You can set this up in so many other ways. Other ways you could have set up the proportion were maybe you did 6 to 9 is equal to 24 to x. That would have been okay. It's not comparing little to big. Remember, this was just one example that I showed you. You also could have set it up as x over 9 equals 24 over 6. And there are a couple of other ways you could have done it too, so all of these are okay. But things that you cannot do, you could not set up 6 over 24 equals x over 9, because 6 is the little triangle, 24 is the big triangle, but then x is the big triangle and 9 is the little triangle. So you see how they're crisscrossed like that? That cannot happen. So when you set up a proportion, you have to make sure that the numerators match and the denominators match. Okay? And there are a couple of other incorrect ways that you could set them up as well. So that was just one example. The last example, F. This one can be a little bit tricky because the triangles are rotated. So when you set up your proportions, again, just go off of, okay, is this the biggest or the smallest segment in the triangle? Or right now, they kind of look like right triangles. So if I say that they're right triangles, that might help me keep things in order. So let me compare 22, which is the hypotenuse, it looks like, of this triangle. So a different way I could set up the proportion is doing 22 over 16, which is a leg of that triangle, to where both of these come from the big triangle, and set that equal to the little triangle. Now, if I chose 22 on top, I need to choose the corresponding side from the little triangle, which is this hypotenuse, which is 11. Over the one that corresponds with 16 is x. So that's going to be 11 over x. So that's a different way that you could set them up, is by doing two separate ratios, one for the big all together and one for the little. Either way, when you get to that point, or even if you did a different proportion than me, we should still get the same answer. If I do 22 times x, it's going to be 22x equals 16 times 11 is 176. And if I divide both sides by 22, I end up with x is equal to 8. So, just to recap, if shapes are similar, that means they are the same shape, right? A triangle is still a triangle, but they're not the same size. They are dilations of each other. The dilation was caused by a scale factor, and as we reviewed earlier, if that scale factor, so on that first page, if the scale factor was greater than 1, then the shape enlarges. Like this example here, right? The scale factor was 2, so my shape got bigger. Whereas in example B, my scale factor was a fraction. It was less than 1, so then my shape got smaller when I divided everything by 2. So that's what causes the shape to become a different size. In order to figure out if it is proportional, the main ideas here were that the corresponding angles have to be congruent and the corresponding sides have to be proportional. I'll say this is probably one of the biggest takeaways from today is similar shapes. Their angles have to be congruent, their corresponding sides have to be proportional. So I hope that is pretty clear and you're off to a great start for this next chapter because this is a very short chapter. We're going to learn about how to prove shapes are similar and do some 2-column proofs, and we're already going to be prepping for a test by the end of next week. So, yeah, that's what's coming up.